Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Alright, today I will share with you about noise performance of analog communication system. We have come to the last chapter, which is chapter 7. Okay, so previously we learned about random noise in analog system. There are 4 types of random noise that exists, and we learn also how to do the characterization on each block. Okay, so for the performance matrix of various analog modulation scheme that we learn in this chapter, to recall, in chapter 4 and 5 we learn about modulation scheme. So in this chapter, chapter 7, we will also learn on how this noise will incur or occur in this modulation scheme. Okay, so there are two parameters, which is C and R, on also S and R. Okay, C and R refer to carrier to noise ratio, and S and R is the signal to noise ratio. So remember, when we transmit the signal or modulated signal, there will always be the carrier and also the signal in the receiver part. Okay, so CNR is defined as the ratio of carrier power to the noise power. Okay, so in specific bandwidth is where we measure the signal. Okay, so how we do this is by look at the spectrum analyzer, or we plot the spectrum of that particular modulated signal. So we can see the carrier and also signal. Alright, so the pre-detection measurement, okay, before comes to the detection, we will measure at the carrier modulated waveforms. So that's why it is important for you to know how to draw the spectrum, or how to find the spectrum of the modulated signal. So we can measure the carrier, measure the signal in terms of power. Okay. Alright, so the second one, SNR, is the ratio of signal power to noise power made at the baseband, okay, before modulation or after detection. So this signal can only be detected before modulation and after detection. So we will have pre-detection and post-detection. Okay, so if in the modulated signal we have carrier, but we don't have it yet after the modulated signal. So after we demodulated, we can have the signal, or before, okay? Of course, since we want to transmit that particular signal. Alright, so we can recall back what is message signal. Okay, so the message signal is the information that we want to transfer. So there will be the transmitter, AM transmitter, and then this AM transmitter will be carried in the form of carrier. Okay, so this carrier will go to a channel, whether wired or wireless. Okay, at that particular point, there will be noise. The noise is called additive white Gaussian noise. As we learn, we know what is white Gaussian noise. So this additive white Gaussian noise is a lump sum, or the lump sum of additional noise that will occur in any channel, whether wireless or wired. Okay, so in the receiver part, so this is the receive signal, we will have a filter. This is H, is the transfer function, and then this is post detection, pre-detection, and then this is post detection, R1T. So after it comes to the demodulator, it will demodulated here. So basically we will multiply by 2 cos FCT, and then we will have the original signal back at this point. Okay, at this point. Okay, so this noise, NIT, is a white Gaussian noise, and the power spectral density, as we learned in chapter 6, will be equivalent to N naught divided by 2. Okay, so N naught divided by 2 is the amplitude. Alright, so um, we will go through this noise, and also what is the noise at this point and this point depends on the modulation type. Okay. Okay, for the first one, if you recall, our first modulation technique is double sideband suppressed carrier. Okay. How to do the SBSC? Okay. This is the modulation type. Okay, DSBSC. But what we have extra is the attenuation or alpha and also the noise. Okay, so when we multiply the attenuation to the double sideband, yeah, double sideband. So this is the DSB, and the coefficient here is from the attenuation values. Okay, it depends on the environment, depends on the gain of the system, depends also on the capability of the receiver, okay, or sensitivity. All right, so this is the noise. Okay, so to measure the power at this receiver, we will call it as the power at the receiver. It will be equivalent to, remember how to measure the power is the amplitude squared divided by 2. So the amplitude of this A N is here. Okay, alpha amplitude squared, alpha squared A C is the amplitude of the carrier is squared, and signal squared. What does it mean? This one is the average. So S squared bar is the average power in the message. So for example, the signal have more than 2 amplitude. Okay, so we need to calculate the average power. Okay, we'll see in the example. Alright, so again, I will show you at the receiver side. The receive signal will receive the modulated signal, okay, with certain amount of attenuation and also a number of noise. Okay, so when it pass to the detection filter, it will reduce the number of noise. The noise will just put in some filter also only, and then it comes to the demodulator. Okay, so this is the demodulator. What it do, it will multiply with 2 cos 2 pi fct. So it will multiply again with the carrier with certain FC, known FC. Okay, we have determined this at the transmitter. And 2 is because the amplitude will reduce by 1 over 2. So 2 is because you want to get the original signal back. Okay, so here it is the signal received or the modulated signal. And then again, we have to put a low pass filter, okay, at the post detection. Alright, so to measure this, how about the noise performance? So we know that at the receiver input, there will be noise. The noise is a WGN. So the noise will be this one, okay? This one, and not divided by 2, okay? The AWGN. And B is the bandwidth. Okay, so how much the length or the size of the signal depends on the bandwidth. Okay, so at the receiver, if you want to measure the C and R, it has to be the carrier power divided by the input power. So this is just now we calculate the carrier power. Okay, and then this is the noise power. So to find the C and R at the input, alpha is the attenuation, alpha squared, AC squared, and S squared bar, which is the average signal amplitude, average amplitude of the signal, okay, divided by 2 and not B. Okay, alright, so at the pre-detection filter output, R1T, okay, so remember we have RT and R1T. So this R1T is at the after filter. Okay, so when we do the filtering, and remember at the chapter 6, we also have this they also remind us about this, which is the narrow band. The noise will be occur at the 2 points. Okay, so this is DSB, so it will occur at the NCT cos 2 pi FCT, and also minus side, just now is plus and minus, and ST sine 2 pi FCT. Okay, so at this point we will have two noise. Okay, and this has to affect the and not beta, the noise power. Okay, so now if you want to see how it looks like, this is the signal. Okay, the signal. So the noise will also occur here and here. Okay. Okay, so at the demodulation part where we multiplied the carrier with 2 cos 2 pi FCT, okay, and also a filter to recover the original signal. So at the detection, which is at the here, YDT, okay, YDT, that means we have been filtered and also post detection, okay, so it will be equivalent to alpha AC ST plus NCT, okay. All right, so at the, if you see this point, AC alpha, so we want to know the post detection, yeah, post power at the post detection is alpha AC squared multiplied by S squared bar, and then the noise power will be double to and not B because it has two bands, okay, and the noise also occur at the quadrature NC and also NS, okay. So where we want to, when we want to find the what is the signal, okay, now we focus on the signal YDT, okay, YDT at the end of the block diagram or at the last point, it will be the signal. So the signal to noise ratio can be calculated by measuring the power at the detection or post detection, which is alpha AC squared S squared bar divided by the 2 and not B, which is the noise at the post detection filter where we have to consider two sides. So it's actually equivalent to the PR is the received power, okay, divided by N not B. Okay, so there are PD and PR. This is the detection and also the received power. So this equation is same with the C and R. This one. Okay, same. Alright. So we can conclude that the SNR for the DSB and the CNR is equivalent, or figure of merit of both SNR and CNR is equivalent to 1 for DSB SC. Alright. Alright, so let's say this example, problem 7.2 in the textbook. The signal consists of two signals, 10 cos 1000 pi t and 5 cos 2000 pi t. The carrier is AC is 10 to the power minus 3. Okay, and the equation or the signal is cos with the AC 100 times 10 to the power of 3 is the FC, okay, pi t, actually omega c. Okay, so you have to divide it by pi, 2 pi, sorry, omega equivalent to 2 pi, okay, using the DSB-SC scheme. Alright, so the white Gaussian noise, this is a random noise, so they already give it to you, generally is 10 to the power minus 12, okay. So the bandwidth is 1 kilohertz, alright. So assume attenuation, alpha equivalent to 1. So that means the signal is perfectly or ideally received without attenuation. 1 means it's the same, right? So the received signal is coherently demodulated after ideal BP filtering. So now we have to find the CNR and SNR. Okay, so you have to Remember what is the formula? Alpha squared AC squared S squared bar divided by 2n naught B. Okay, you memorize the formula and then you identify the signal. So here is the tricky part where we have to calculate the S squared bar. S squared bar is equivalent to the amplitude of the signal average. Okay, if it has two signal, okay, just now is 10 and also one more is 5. Okay, where I got this one is from here. Okay, the amplitude of the signal. So you want to find the average of the amplitude of the signal. Okay, so we squared and divided by 2. So S squared bar is equivalent to 62.5. Okay, AC squared, just now AC is 10 to the power minus 3. And alpha is 1, B is 1 kilohertz, and naught divided by 2 is 10 to the power of 12. But now we just want n naught, so it has to be multiplied by 2. Okay, so be careful with the given values of white Gaussian knife here. Okay, so we want n naught, so it has to be multiplied by 2. Okay, we substitute here, we get the real number 15.625. Okay, so since we want it in dB, okay, the CNR in dB, we have to change into 10 log this one. Okay, we will get these values in dB. Okay, so make sure the values and the okay, the next one is SNR. So we know in the SBSC, the SNR is equivalent to CNR. So we just put this equation, same. So it's equivalent to 41.93 dB. Alright, so the second type of modulation is single sideband. Okay, I know the second one we learn is conventional AM. Okay, but we just follow this slide. Let's see what is the noise performance of SSB. Okay, let's say we have USB. Okay, for USB, the equation or the formula is AC divided by 2, ST multiplied by carrier CT minus for USB S hat, which is the Hilbert of the signal, multiplied by the carrier Hilbert of the carrier. So Hilbert of the cos is a sine. Okay, so of course you have to include the noise and also the attenuation level. Okay, usually given by the system, or we can calculate, but in this question is given. Okay, so the signal power at the pre-detection filter means we have to square the alpha AC and also S. Okay, so 2 AC squared divided by 2 is this one, and also this one we include the divided multiple by 2, so we got this formula. Okay, so again the Pn, which is the power of the noise, is measured by N naught B. Okay, this one only one side. Okay, alright, so we substitute the PR and PI. So this is the value of the PR. Okay, so this is the value of the noise of the power of the noise. Okay, so at the pre-detection filter, again we will have two parts, this one, and at the post-detection we will include upper sideband only. Okay, so at R1T, which is the after the filter, we multiply with carrier and also a filter. So this is at the post-detection low-pass filter. Okay, so at the post-detection, we substitute the amplitude of the signal squared divided by 2 and identify also the power at the noise. So we will substitute the SNR. Again, SNR will be the power at the post detection divided by the noise power. Okay, so post detection will be the signal noise because we have multiplied with the demodulation part, or we have demodulated it with 2 cos 2 pi FCT. Okay, so again for SSB, the SNR is equivalent to CNR. Okay, with this formula. The difference is here. Okay. For double sideband is divided by 2, this one divided by 4. Okay, so this is due to the equation of the modulated signal, right? Okay, so again, to ease or to make you more understand, we put a signal, two signal with the amplitude of 5 and 2. This is the carrier. The amplitude is 1. Okay, using SSB with white Gaussian noise, given value, bandwidth 3.5, and the attenuation is 60 dB. Okay, so be careful. This one is 60 dB, okay, not in real number. Okay, the receive signal is coherently demodulated. So if demodulated, we can measure the CNR and also SNR. Okay, so to determine the CNR, we use the formula alpha squared AC squared S squared bar divided by 4 is the PR and N naught B is the noise power. Alright, so for the S squared bar, we have to find the average of the amplitude. Okay, and AC is 1, and here alpha is 10 to the power minus 3. But here they said that the power is 60 dB. How to get dB to real number? We have to use the attenuation formula, which is power in dB. Okay, equivalent. So this is for the attenuation, yeah. 20 log 10 A. Okay. So how to find A? Because here the calculation is in real number. So 60 divided by 20, okay, equivalent to log 10 A. So you have to do the anti-log. Okay, so for the attenuation, you have to remember it will be minus. Okay, so means here minus 60 divided, okay, equivalent to A. Okay, so you get 10 to the power of minus 3. Okay, so just substitute in the equation and then you get the number changed to into dB. So SNR and CNR for single sideband is the same. So the answer is the same. Alright, the third conventional AM modulation scheme. So for this one, it's quite long and complicated because we need to include this formula. Okay, so please recall this is the formula for the conventional AM. For conventional AM, there are extra information, which is the modulation index and also the normalized signal. Okay, so just don't be panic. So we just have to consider all this as the amplitude. Okay, so this is the amplitude squared and divided by 2. Okay, to find the power. Amplitude squared divided by 2, so you get the received power. Okay, so what you have to do now is to find the message signal at the baseband is and not B. So you just have to divide power R squared power, which is amplitude squared divided by 2, and also the and not B. Okay, so to alert you, this is the normalized signal. Okay, the normalized signal is, again, you have to find the average signal divided by the P max squared. Okay. Okay, so to find the noise performance, you have to, this is to explain you the pre-detection, and then at the demodulated signal, we have, which is YDT, the original signal is we multiply by cos 2 cos FCT. Okay, and then we got this equation as the final detected signal. Okay, so you just have to divide, okay, this one and the 2 and not B. Okay, so for the conventional AM, we will have two sides, so we consider this 2 and not B. Okay, so now just now we have seen the CNR and SNR, so the only different is the mu. Okay, mu is the attenuation, the ratio of the CNR and the SNR. So that makes the difference of pre-detection and post-detection at the conventional AM. Okay, so since mu is less than 0.5, okay, the SNR of the conventional AM, okay, this is actually conventional AM, is, okay, 0.5. If you change into dB, is at least 3 dB poorer. So means that if we use the conventional AM, the quality of the signal and the carrier will be lost about at least 3 dB, okay, compared to DSB and SSB. Because SSB and DSB, the CNR and SNR is equal, which is the figure of merit is 1. Okay, so means it will be perfect as much as the carrier at the post-detection and the pre-detection. So this is the only difference for the conventional AM, where we have the mu equivalent to MA squared SN squared average or bar divided by 1 plus. Okay, so certainly it will have a we can say a loss or attenuated. Okay, so another problem is, again, we have two signal, which is the amplitude 1 and 0.5. This is the carrier. So now we have AC equivalent to 2 using conventional AM, and we have modulation index. So this P max will be used for the measurement of normalized signal, which is S squared bar divided by P max is equivalent to the normalized signal. And then again, here they define the power spectral density for the noise is 10 to the power of minus 8. Okay, then with 3 and alpha is 1. Okay, now calculate the CNR and SNR is easy as long as you can remember the equation. Okay, we substitute the values also I've explained here. This is to find the normalized signal, right? So this is AC is 2, squared become 4. Then we straightforward, and then we can find the CNR. Okay, how about SNR? We have to remember that it's not the same. The difference is this mu. So we have to calculate the mu multiplied by the CNR to get the SNR. So mu is not difficult also. You have to remember this equation and then multiply by the CNR, you get the 38.25 dB. Alright, so this is the continuation of the chapter 7, but I'll just stop until the noise performance. So, so this is, I will just cover until here for chapter 7. So inshallah, if you have question, you can ask me. It's just that you have to memorize the equation, understand how you get the equation and substitute, and then you can measure the CNR and SNR at each modulation scheme. Alright, so that's all for chapter 7. Thank you very much. Assalamualaikum warahmatullahi